Okay, here we go. So yesterday we talked about these London dispersion forces. And I was starting to give an explanation, kind of the quintessential explanation that I'd like to give as far as a molar mass being a difference, okay? So when you look on the periodic table, if you look at my fancy one in here, the periodic table, I have chlorine, and we have chlorine bonded to chlorine. We have bromine bonded to bromine, and we have iodine, because these are Brinkelhoffs, right? So these are molecules here, okay? If we look at my periodic table, it's actually color-coded. So it tells us at room temperature that this ends up being a gas, which means that it has very few or no intermolecular forces at all, okay, between the molecules. They're there, but they're so spread out that they don't have much of an effect. Okay, that disruptive force is greater than the cohesive, and so they're in a gas. This at room temperature is a liquid, and this is a solid. Okay, now these all have the same shapes. They all have 6 valence electrons around here on the outer. On the outside of these are 3 lone pairs per each one. So everything is essentially the same. What's different is the molar mass. And it's really not even the molar mass that's the difference. The difference truly is if the molar mass is higher, that means that it has a greater number of electrons. Okay. This is just an indicator of this, but this is what really matters, is the greater number of electrons. Because remember, it's that those electrons can kind of move and slosh back and forth. I gave you kind of the analogy of the glass yesterday, and if you walked across, with a glass of water, you'd be okay. But if you try to do like a tote of water, it'd be sloshing everywhere. That's the same idea. If we look at the number of electrons that this has 34 electrons. This has 71 electrons. And iodine would have 53, so that'd be 106 electrons here. Okay? So as we increase the number of electrons that are able to kind of slosh from side to side, we increase that attractive force, because we've got more negatives over here. Let's say if it's sloshed this way, this would be more positive over here. And so because of that, it's able to be attracted to another molecule of iodine, and then to another molecule of iodine, and so forth and so on. Those attractions are strong enough so that this forms into a solid, and this thing doesn't move around, as opposed to a liquid where these intermolecular attractions are weaker. You don't have as many electrons. They're weaker here. And so here, because this is weaker, it's able to move past and kind of slide around. But there's still some attraction. And then when you get to the gas phase, that attraction, the particles are too far apart, and so you're not getting that attraction anymore. All right, so that's London dispersion forces. If we were to rank these in order of increasing boiling point, remember, if we look at the structure of these are all nonpolar. So they're all in the same format. I'm just going to put X's here, okay? So for the place of X, for this one, you put chlorine in there. For the place of this one, you put bromine in those spots. And for the place of this one, you put hydrogen in those spots. Okay, so structure is exactly the same. Which one of these is going to have the lowest boiling point out of the 3? Why? Correct. Okay, so the molecular mass for this is 16. Okay. For this one, 4 times 35.5. is 142. And for the bromine, 79.9. Oh, but I forgot to add in the carbon. Hold on. So this is, strike that. This is 331.6, and this would be 12 more, so 54. So that's 154. Sorry. Okay. So in order of increasing boiling point, we have CH4 listed first. Then what would come? Yep. And then the CBr4. Does that make sense? Well, that's good news. Okay, good. Ready to go? Okay. So dispersion forces also have a magnitude for the shape of the molecule as well. So this N-pentane here, because it's spread out more, there's more areas of contact here versus this. Even though they have the same chemical formula, they're just shaped differently. This has more contact area. So because of this, this one's going to have a greater dispersion force. So you also have to look at the shape of these sometimes as well. Okay? All right, next one. Dipole dipole. So when we were talking about London dispersion forces, those were not permanent. They were temporary. So if I'm just going to flash back up here to this. It's a temporary dipole. Temporary means that it happens and it's gone. It happens, it's gone. It happens, it's gone. When we get into this dipole, that is permanent. It is always there. And it has to do with those electronegativity differences that we talked about in chapter 8. And it also has to do with the shape of the molecule and the distribution of those electrons. Getting any of this down, Ernesto?
Oh, no,
You're just letting it soak in?
I was just letting it soak in.
Just diffusion. We talked about that yesterday. Yeah. Just letting it diffuse in. You're going to listen to my lecture later because you love my voice. All right. So again, this is permanent dipole. If we look at something like sulfur and hydrogen sulfide here, this has these two lone pairs of electrons. Remember, if something has these lone pairs of electrons on the central atom, it's always going to be polar. Okay. We talked about the charge and how we can indicate that. Okay. This is the positive end of that molecule. This would be the negative end. Sometimes that's shown with this little S with a kind of backward kind of loop on it. Okay, it's some sort of Greek symbol. Don't ask me which one. But sometimes you'll see it shown like this as well for charge. Okay. Hey, there he is. Okay, thank you.
Thank you.
we've got these permanent dipoles that are set up on here. Okay, so no matter what's going on with this, these are always going to have charged ends to it. Like I said, remember, if you have lone pairs of electrons on that central atom, it's always going to be a polar molecule. Don't even have to think about it. If you're remembering back to chapter 8 when we did that stuff. All right, so you're always going to have a positive end and a negative end to this molecule, which means when it comes around another molecule like it, they're going to orient themselves so that those attractions and repulsions, the attractions are maximized and the repulsions are minimized. But that's going to create an attractive force here. And when we get those attractive forces, that's what's going to cause an increase in our boiling points. It's going to increase our melting points. So something that has dipole-dipole forces typically will have a higher boiling point than things that don't. Now, dispersion forces can override that occasionally, but that's kind of a general rule. There are exceptions, of course. This doesn't affect substances in the gas state because the particles are too far apart for that attraction to work. All right. Again, you're going to look for those polar molecules. If you have a nonpolar molecule, you will not have dipole-dipole forces. Okay, so dipole-dipole forces only occur in polar molecules. Remember, we can also look at differences in electronegativity to figure out if we've got like a polar or a nonpolar bond. So that sometimes helps us also determine if we've got polar molecules. Okay, acetone is a good example here of this. So here is acetone's symbol, or formula, excuse me. So let's figure out with acetone, and acetone is a polar molecule. Okay, it is polar. This is polar. So now let's look at the molecular mass for this. We would expect that acetone would have a higher boiling point than water. Okay, because the molecular mass of this is 24, 6, 30, 30, 12, 16, and 30. I think it's 58. Okay. Do that right? No, that's not right. That's not right. 24, and so that's 30. And then I've got the 12 and the 16. Yeah, it's 58. Sorry. So molecular mass is 58.0 for this, and for water, it's 18.0. So if we were just looking at the fact that this acetone had a greater molecular mass than the water, we would expect that acetone would have a higher boiling point. Correct? Now, ladies, have you ever had fingernail polish remover? What happens if you leave the lid off a fingernail polish remover for a while, overnight? You come back, do you still have fingernail polish remover? What happened? It evaporated, right? Okay. So the boiling point of acetone is actually lower than water. Exactly. Twist your head and go, why? Because there is one more intermolecular force at play here that we haven't talked about yet. Okay. So acetone has two intermolecular forces at play. It has those London dispersion forces, and it has the dipole-dipole forces that we just talked about in the previous slide. Water has London dispersion forces, it has dipole-dipole, and it has one more. And it's that one more that makes the difference. Okay, and that's what we're going to talk about next, which is called hydrogen bonding. Okay, now let me be very clear to you. Hydrogen bonding is not a bond between two hydrogens. Okay, I know that's what it sounds like. I get that. Okay, it's not even a bond between like a hydrogen and something else. Okay, that term, hydrogen bonding, I think is extremely confusing for people. It was for me for a very long time. Okay, so I want to try to dispel this myth. It's not a bond between hydrogen and another atom. Okay, it's going to be between two different compounds, or between two different molecules of a compound. And I'm going to explain to you kind of the rules here for that. Okay, so hydrogen bonding, hydrogen on one of the molecules is attracted to an unshared pair of electrons on an adjacent molecule. Both the hydrogen and the unpaired shared pair have to be on the phone. Now, what does phone mean? Either a fluorine, an oxygen, or a nitrogen. I'm going to give you kind of a checklist here in just a second so you can write these down, how you can figure it out. Yeah.
Do you have a paper copy of this?
Yeah, you were gone, weren't you? I'm so sorry. Yeah, there's one up here. I'm sorry. This is actually one of my absolute favorite units of the year to teach. I love teaching about this. And so I get really kind of wrapped up in it because I think it's really kind of cool. I mean, it just explains so many things, you know? So I get excited about it. And then I forget to give papers out to people who've been gone. My apologies. So hydrogen bonding, it's so fun. No? Not feeling it? Kim Cat? No? I don't see anybody getting excited about it. So who's on the phone? Hydrogen. Still no? Still not feeling. Do you need to get more stuff down off of here? Did you have to write anything down on here? I don't know. I'm not following along. No? Everything's good? Okay. All right. Anything on here you got to write down? No? Okay. So, like I said, it occurs between a hydrogen and a polar bond and a polar bond and a non-bonding electron pair on a nearby small electronegative ion, usually fluorine, oxygen, or nitrogen. So what happens is if you have this, okay, you're going to end up with a hydrogen bond between here. Hydrogen acts kind of like a proton then, because it's gotten its electrons stripped away over to this side. And yeah, that gets into that. I want to add in, let me add in a slide here. I don't know. I'm going to add a slide in. Blank. All right, there we go. All right, so what is your checklist for this, for hydrogen bonding? Number one, is there hydrogen in the molecule? Okay, so for example, when we have our oxygen bonded to two hydrogens here, okay? And I'm going to do another example over here of one that's not hydrogen bonding, just so that you have kind of a juxtaposition between these. So for this one, both of these would be a yes, we're good. Okay. Number two, is there fluorine, oxygen, or nitrogen with at least one lone pair of electrons. So for this one, for our water, we have these lone pairs of electrons here. For this guy, though, we've got lone pairs of electrons, but what's the problem? It's not fluorine, oxygen, or nitrogen. So this guy's out. This guy is still in play. Okay? So if that's the case, then we have hydrogen bonding for this guy. Okay? And and that's going to lead to a, now we've got not just LDF, because everything has LDF. We don't just have our dipole-dipole, because that's in all polar. Let me see if I can spell here. Okay. We don't just have dipole-dipole, because that's in all polar things. But now we also, in addition to that, have hydrogen bonding. Okay. And the way that looks, do I have, yeah, I do have pictures of that coming up. So let me just get the good pictures that somebody can actually draw has. Okay, so, but now we have the hydrogen bonding. Now, what does that do? Okay, hydrogen bonding will increase our boiling points, but it also is what causes ice to float. I mean, think about this. Most of the time when you have a solid, right, that solid, if it's in its liquid form, will sink to the bottom, right, because it's more dense. But that doesn't happen with water, does it? What happens with your ice cubes? They float, okay? So there's a reason for that, okay? I mean, think about, like, you know, all kinds of stuff with ice, with different things. You know, it's kind of cool that, like, that's one of our weird exceptions, you know, to the rule. I know. And this is where I get geeky in chemistry. I'm sorry. My love of chemistry starts to kind of flow through here. So yeah, it's just really cool. So it's less dense in than its liquid form. Okay. The reason that this happens is because in that solid form, it arranges itself, and we essentially get these little cavities that form in here. This little extra space that forms inside of there. And because of that new structure, it takes up more volume than its liquid form, which is rare. Typically, a solid form is going to be more compact than a liquid form, right? When something melts, it takes up more space. But that doesn't happen with ice. And so that, because its volume increases, its density decreases. Because remember, density is mass over volume. Well, the mass didn't change just because it changed state, but its volume did. If the volume goes up, the density goes down, because if you're looking at a ratio there and that bottom number gets bigger, then that value gets smaller. Yeah? Okay. So because of that less density, it's going to float. So when we look at water here, we end up with a solid form that looks like this. Here, this is taking up less volume, so that's actually more dense. And then you've got your gas form. So in the liquid form, the structure is going to collapse due to those increased motion of molecules, but it still has some hydrogen bonding. Okay, and that is why you end up with this crazy strong surface tension for water. So if you look at water, that's why your insects can walk across water, is because of the strong surface tension. During the summer, If you have like fruit flies in your kitchen, sometimes you get those in the kitchen during the summer, right? What you can do is you can take a little cup of like apple cider vinegar or something sweet. You can use pop, whatever. Okay, something that'll attract it. Put 1 drop of dishwash soda or dishwashing liquid on it. What dishwashing liquid does is it messes with this hydrogen bonding so that surface tension becomes weaker. So when the fruit fly lands on there, instead of floating and drinking the liquid, it can't float anymore. It doesn't, the surface tension isn't strong enough for it to stand on there, and it falls right through and it drowns. And so that's how you get rid of your fruit flies during the summer. Now, problem is that some of your flies might still be able to fly away, but you know, they might even get sunk in there too. But they have stronger wings, so sometimes they can pull themselves out of it. So hydrogen bonding is the strongest of these van der Waals forces. It's going to be responsible for these really high boiling points. Okay, and that's going to give it really high boiling points. Good? Okay. So if we go back to this graph, remember this is what we started with yesterday in class, and we talked about how this was kind of a strange trend here where we started out and this was kind of, you know, like, okay, I can kind of see that. Yeah, we start out here and then we're moving up. All right, get that. Remember with these, we kind of looked at some of these at the beginning. These are all nonpolar, so they're going to have really low boiling points because all they have is London dispersion forces, right? When we start looking at these, okay, and start looking at their structures, we look at our NH3 here. Okay, and we start checking off boxes. Well, we know that this has London dispersion forces. Because of this lone pair of electrons on the central atom, it has dipole-dipole. And if we start looking at our hydrogen bonding, does it have hydrogen? Yes. Does it have nitrogen, oxygen, or fluorine? Yes. And is there a lone pair of electrons on that nitrogen, fluorine, oxygen, or nitrogen? Yes. So this also has hydrogen bonding with it as well. Okay. So this has 3 different intermolecular forces at play for this NH3 here. Okay. If we look at our pH3, if we go over here and look at pH3, this has our London dispersion force, because remember, if you're asked what intermolecular forces it has, automatically write down LDF. Okay, London dispersion force, because everything has this. It has a lone pair of electrons on the central atom, so it's dipole-dipole. It has hydrogen bonded to that central atom, but the central atom isn't oxygen, fluorine, or nitrogen, is it? So this only has 2 IMFs versus this where it has 3. So because of that, its boiling point is going to be lower than this guy. So the hydrogen bonding that occurs in these 3 is why the boiling point is kicked up so much higher over here, and then it plummets and then increases. Now, why does it increase as we move up here? Well, if we look at what comes after this, ASH3, what's the difference between these two? They both have London dispersion forces. They both have dipole-dipole. What's the difference between these 2 molecules? Which is, it's not really, the weight is an indicator of the number of electrons, okay? So when you get into AP, that's what they're going to want to know. They're not going to accept molecular weight as the answer, okay? They want to know that this guy has more electrons. And because it has more electrons, it's more polarizable, okay? It has stronger poles here than it does here, okay? And that's what they're going to look for, okay? The weight is an indicator, so good, okay? But you've got to connect that weight over to the electrons to be able to get actually points on the AP exam. Make sense? Okay, so that's what I wanted to do as far as explaining that. Now, hey, how are you? You need Gabe? Okay, he's right there. Okay, you can just hand it to, if you don't mind. Okay. So ion-dipole forces are the last ones that we're going to talk about. Now, these are not van der Waals forces. These occur between a molecule, which is where your dipole is, and an ion. Okay? So your dipole is for your molecule, and that's a charged end of your molecule. And then your ion, remember your ion has a charge with it as well. That's why it's an ion, because it has a different number of protons and electrons. Remember that? Okay. So you're going to get an attraction between those. So when we look at water here, remember if we've got a water molecule, your water molecule has a positive end. That's this end with the hydrogen on it. And it has a negative end up here. Okay. So if you have a positive ion like nitrogen, or sorry, not nitrogen, sodium here, okay, this is positive. If this comes around water, water is going to orient itself so that that nitrogen, why do I keep saying nitrogen? That sodium is going to get surrounded by the oxygen end of the water. Chlorine has a negative charge, so that chlorine is going to get surrounded by the hydrogen end of that water. And what happens when you have water? When you have water and you add salt to it, what ends up happening is it ends up taking that sodium chloride and essentially pulling it apart, okay? This attraction of the water end, the positive end here, is stronger than the attraction between these two here. So when water comes along, this guy gets pulled away from that crystal here, and these water surround it. This guy gets pulled over here, and these waters surround it. And you end up with one of 2 situations. Either you end up with more water than you have ions to surround it, which is called a unsaturated solution. You can add more salt in there. Or you end up with a saturated solution. So you end up with more salt crystals in there than you have water. So you don't have enough water to be able to surround every one of those ions. And that's called a saturated. So that's where your water, there's salt, you would end up with salt down at the bottom of that material. And we'll get into more of that when we get into solubility. All right. So this is just kind of a flow chart. And I need to add on to this. Are hydrogen atoms bonded to the nitrogen, oxygen, or fluorine, and the fluorine, oxygen, and nitrogen have a lone pair of electrons. So they needed to have that in their little flow chart, and they didn't. So I like to add that in because that becomes critical. Okay. So see if you can rank these in order from lowest boiling point to highest boiling point. So we got barium chloride. We have hydrogen gas. We have carbon monoxide. We have hydrofluoric acid, and we have neon. All right. So this is an ionic, This is an ionic compound here. So we know that that's going to have a really, really high boiling point. Because remember, that's going to be a solid at room temperature. Okay. So we know that that's going to have a high. This one, if we look at the bonding here, this is nonpolar. Okay. So that's going to have only LDF here because it's nonpolar. Okay. This isn't bonded to anything. So that's only going to have LDF as well. There's no lone pairs of electrons. There's nothing going on here. So now we need to compare these two. So both of these, you know, they're just LDF. Which one's going to have a higher boiling point? Well, we also need to put this in here too, because carbon monoxide. So this one, although, well, that's carbon monoxide though. Is that polar? I'm starting to question myself here. Yeah, it's polar. Okay, yeah. But only because of the electronegativity difference, because this also has, oh, I guess this is triple bonded. I'm not thinking right. So we do have some electronegativity differences here. We also have mass difference here too. So this guy, the mass of this is 2. The mass of neon is 20.2. Mass of this would be 16, and 12 is 828. So the mass of this is also higher. Plus we got an electronegativity difference here. This is 3.5 and carbon is 2.5. So you got electronegativity difference of 1.0. So this is actually ends up being a polar molecule because of that electronegativity difference. So this is actually polar here. So if it's polar, that means that it's not just going to have LDF here. It's also going to have what? Dipole dipole, right? Okay. So we know that these two are going to come first. Which one's going to come ahead? Well, the hydrogen's going to have the lowest boiling point because it's got, all right, we'll finish that up tomorrow. You've got a pivot lab. We'll finish the notes up on Monday, but you do have a pivot lab that's assigned to you or will be assigned to you. That's due by Monday. So you've got all weekend to work on that. Okay. Have a good weekend. Or I guess it's due on Monday. Try to get it done Monday. I want it by Tuesday at the very latest. So close to being done. So close.